All right, hi everyone. My name is Avery, and we are going to go over the basics of assignment 2 HashMap, as well as the relevant C++ behind it. So just a quick overview of what assignment 2 is. Assignment 2 essentially has students implement a hash map. Now, the hash map assignment is definitely not as flashy as the other assignments, but what we found is that this assignment does a really good job with focusing on the basics, and especially the basics of class design, and then driving home a lot of the important points that we'll discuss right now. So I'm going to quickly go over this assignment. This assignment is fairly short in that what essentially happens in this assignment is we give them a starter code, which is a complete version of a hash map. So that we give them a hash map, which is fully functional. Okay, but this is the hash map which a student probably would have written in CS106B. Okay, so you can imagine that everything from CS106B, the basics of class design, everything there is all given in the starter code. What is not given in the starter code is the material relevant to CS106L. So in the 4 milestones that the students have to do, they will be implementing different, they'll be extending the hash map. There are 4 milestones. Milestone 0 is just learn about hashing and also to examine the starter code and test harness. But then in the 4 milestones later, only 3 of them involve coding. So in total, it's around 100 lines of code, not too long. And then milestone 3 in particular, we made it optional because of the recent things that have been happening in the US. Okay. Because milestone 3 was optional, most of you were assigned students who completed milestones 1, 2, and 4. Okay, so we'll be going over how to grade those. In total, it's not a lot of lines of code, so we hope it will be fast. Okay, so let's just quickly go over some of the. I'm going to go through this milestone by milestone, and I'll also simultaneously cover the concepts relevant to that milestone. So just a quick overview. Let me actually switch over to the code. Okay, so you can actually see over here. Let's see, is this the code? Let me see if I'm showing the code right now. Yes, okay. So as you can see over here, we are looking at just double check one more time. Yes, I am sharing the correct code. Okay, so yeah, this is the starter code as well as the solution is added at the very bottom. But you can see here that we give them the starter code, which looks like this. It is super well commented. But essentially, students have to implement a hash map that is a template. Okay, so when you use the Stanford library, you'll know that when you write the word hash map, you also put the key and the value type in the angled braces. And then how that is internally implemented is you add this template keyword at the very top. Okay, so kind of like just like templates and regular class design, you basically combine them together. You can use the K and the M in the place of wherever you would have before said like it. Yeah, so you can see that all the parts of a hash map are all here. So you can see a constructor. This is what we call this is a special constructor that we'll talk about later. This is a destructor. There's a size, there's an empty. There are a lot of like extra wells and whistles here, like the no except and inline. Those aren't super important. Load factor, bucket count, contains, clear, insert. Okay, insert's kind of interesting, so I'll actually go over that a bit. Erase, at, debug, rehash. Okay, so these are the functions that they were given. Well, they weren't fully given rehash. We gave them like part of the rehash, but then they had to finish the implementation of rehash. In milestone 2, what they'll do is they'll implement 4 different operators. So there's this operator, the bracket operator. For a map, what the bracket operator does is it just takes in a key and then it returns a reference to that value. There's also the stream insertion operator. This is also how you print to see out, how you print your hash map to see out. Oops. Recall that hash maps are unordered, so when you print to see out, the key and value pairs are not in any particular order. And then there's also the equals and not equals operator. Okay, so that's milestone 2. I'm not going to go into milestone 3 because that is extra, although I might. Maybe the last part of the video, optionally, I'll go over what the milestone 3 is. Okay, so just a quick overview of each of these functions. Constructor creates a hash map, an empty hash map. Now, what you'll notice interesting is that these the key value pairs, we also have an extra hash type here. And the key thing about that is just that the hash map, By default, it uses the default hash for the value k, but you can also provide your own custom hash function, okay? So that's kind of cool. Usually we pass them in as lambdas, so you'll actually see an example later. Cool. All right. What is this? This is called a type alias, and they are essentially, if you've ever used pound defines, they're basically pound defines, but they're nicer in that they'll do a lot of type checking for you. They're a new invention of C++11. So anywhere where you see type value type, it really means this thing. Okay. Yeah. So a hash map stores pairs of key value pairs, pairs of keys and values. Cool. All right. So hash the constructor, as you'd imagine, it uses the default number of buckets and also the default hash function. So if you don't put anything in here, then by default it creates the buckets in the hash function. How it's implemented, you can actually see that here. Don't worry too much about what this is. This is called a delegating constructor. What this does is it basically calls this other constructor, which I'm going to go into right now. The other constructor, this one, is this is the, you can kind of think of this as this is the constructor which you can pass in exactly what your bucket count should be. So how many buckets your hash map uses, and then what hash function you want to use. Okay, by default, you can see there's a default value. By default, if you just put in the bucket count without pushing the hash, it uses the default hash. Okay, yeah. How it's implemented, we use this thing called a member initializer list. Essentially, it's setting each of the private members. So the private members in our hash map are the size. We store a copy of the hash function, and then we also store the buckets. Okay, I'm not going to go into a ton of detail about what the internal structure of hashing is. I'm sure you've all taught 106B, so you know that the easiest way to implement hashing is you can actually just create a bunch of buckets, and then each bucket is a linked list of all the elements. To see which bucket a key value pair goes into, you basically hash the key to find which bucket it is in, and then you just go through the buckets to find it. Okay, cool. Right, there's a size. Size is very straightforward. You declare it as const since you don't change anything. Empty is also very straightforward. Load factor, exactly what is in CS106B. You can calculate the load factor here. Students don't have to implement this. This is the starter code. Bucket count, how many buckets there are. Okay, contains. So the STL unordered map doesn't have a contains function, but it's coming out in C++20 anyways, and students are familiar with this from the Stanford library, so we're going to implement that anyways. So you can see what the contains function is. Okay, so the contains function calls a helper function called find node. So we'll see what that function does. Find node finds finds the specific node that contains the key value pair, and then in particular, it has if you get the key value pair, if you get the second one, that will give you the actual key value pair, the actual node for that key. So just check if it's null pointer. Clear is very straightforward. Clear, how you implement clear is you go through all the buckets, you do a for loop over all the buckets. Each bucket is a linked list. So the element inside that bucket in the vector is a front pointer, and then you can use that front pointer to just go through the linked list, go through each node one by one, and you free it. Okay, cool. All right, insert. Insert's kind of interesting. So recall that when you use an unordered map, when you use insert, you have to put in the key value pair as a pair. So notice here that we're actually putting, if 3 is our key and Avery is our value, then this thing creates a key value pair, and then we insert that into our map. The functionality of an insert is kind of interesting. It's a little bit different than the Stanford one. When you call insert, what it does is it tries to insert this key value pair. If the key doesn't already exist, then it will insert the key value pair. Okay, and then the return value is just a pointer to that pair that we just added, as well as a Boolean true. However, if 3 already is in the maps, for example, if we added this and then we tried adding 3 Anna again, then because the key already exists, the insert function won't do anything. It's not like the Stanford one where it will replace the original key value pair. Here, it just won't do anything. Okay, and then the return value would be a value type pointing to the key value pair that it did find, which is 3 Avery, and then it will return false here. Okay, so it kind of combines the functionality of contains and the actual code to insert a key value pair. Cool. Erase, pretty simple, takes in a key and then returns true if it was able to erase it, false if it didn't find the key. Implementation also uses that find node thing. Now, the find node function, which is a helper function, is special in that it returns two things. It returns a pointer to the previous node, and it also returns a pointer to the current node. You can kind of guess why it does that. The reason it does that is because to actually erase something from a linked list, you have to rewire the previous pointer. So that's why here the find node function returns both. And when we call, oh, that's the at function. Let's look at the erase function. Where's the erase function? Oh, here, yeah. Yeah, in the erase function, you can see that it returns the previous and the node to current. And then as part of erasing, it has to rewire previous, or previous next, actually. It has to rewire that to node to erase. There's a lot of bit about like linked list logic here, handling the edge case of if the key was not found or if the key was at the beginning of the linked list, but you can read through this yourself. I'm sure you're all very familiar with linked lists. Cool. So that's that function. The at function is kind of like the bracket operator. So it basically finds the node. It finds the node and it returns the mapped value. Okay, it's a reference. So that means that we're allowed to use that reference to modify stuff. Like we can get the mapped value at 3, and then we can change it by setting that to Avery. That will change a key, the key with 3. It will change its corresponding value to Avery. Cool. If a key is not found, out of range exception is thrown. Remember that auto insertion is not supported in the at function. Instead, operator bracket, which will be implemented later, that's the one that supports auto insertion. This is consistent with the semantics of the STD unordered map. Okay, moving on. The find node function, just recall, it returns a pair of nodes. It returns the node that was currently found. That is the key itself. And it also returns the node right before it, or null pointer if this key value pair's node is at the beginning of a linked list. Okay, you can read that implementation. There's a debug function that you don't have to download any starter code because we've graded functionality for you, so you don't need to look at that. All right, and that's a good overview of the starter code. Okay, yeah. Just the last thing about the starter code is that in a lot of the code you'll see this kind of thing happening. If you graded for Keith, this will seem vaguely reminiscent, where one of the members that you're storing is the hash function itself. That's this thing, and then it's a function, so you can call it as if it was a function. So when you call, you always hash the key, and then you modify the number of buckets to get the index in the bucket in which you are using, in which the current key is part of. Okay. All right. Is there anything else we need to cover? Let me switch over to, and then while we're at it, I'm also going to switch over to the slides, just to give a quick overview if there's anything else we should cover about conceptually, because I also want to help you guys learn some C++. So, okay, you all know everything about class design. Yeah, so yeah, one thing to note is that everything we wrote is put in actually, we don't use namespaces, but namespaces are essentially, you can actually organize code into different namespaces. Everything from the STL is from the SC namespace, and then if you wanted to implement your own vector, for example, you would have to put it in your own namespace. Now, when you implement a normal class, you put the class definition, the headers, in the .h file, and you put the implementation in the .cpp file. Your .cpp file is the one that includes .h file, and then when you actually use vector in your main function, you would include vector.h. When you use a template, though, it's a little bit different in that you have to put both the class definition and the implementation in the .h file. The reason for that is because templates aren't real functions, so when the compiler does the whole linking thing, it's not able to find this if you put it in a separate file. Okay, but then there's an alternative to this, and that's actually, you can actually still put it in the .cpp file and just make sure you include the vector.cpp. This is very uncommon, and it's non-standard in industry, but students complain that the .h file is too long, so this is what we did for the assignment. Cool. All right. Syntax-wise, the interesting thing you'll notice about the syntax is that when you actually implement each function, you have to use this template type so that the compiler knows that this is part of the vector class with specific template values. Cool. Nothing super interesting going on here. Okay. Okay, type aliases. I briefly explained this already, but type aliases are basically pound defines. Okay. Now, what the nice thing is, if you put a type alias within a class, then you actually reference that alias using the actual class name itself. So recall that when you use iterators, usually use auto, but before C++11, you'd have to use this weird iterator type. And the actual class, the actual type of that iterator is not this name, but it's just because the vector class has given it an iterator. Okay, and then the nice thing is then you don't really have to think about what the actual type of that iterator is. You can just use this alias iterator. Students don't have to add any aliases, so you don't have to worry about that. We're not going to worry about type name. Cool. All right, not important. Okay, cool. Let's go over the implementation of Rehash, which is milestone 1. Okay, so in milestone 1, give me 1 second, let me pause. All right, back to the recording. So let's look at the implementation of Rehash. So the idea of Rehash is that currently your hash table has a set number of buckets. And what we want to do is we want to change that number of buckets. Now, the moment you change the number of buckets, all the elements must go in their right place again. Okay, so in this function, they're given the new number of buckets, and they have to essentially move all the elements, all the nodes, to the correct bucket. Okay, so we're going to create a new vector of nodes called a new bucket array with size new bucket count. And then we're going to go over all the buckets. So remember, all the buckets are linked lists. We're going to go over all of the linked lists. We're going to go through each linked list. And then we're going to move each node to the correct new bucket. Okay, so yeah, the old buckets array is just called buckets array down here. And then the new buckets array, that's the one that we're moving all the buckets to. So we're going to go through all the linked lists. We're going to get the key value pairs. We're going to hash the key, modify the new bucket count to get the index. And then we're just going to do some linked listing where we're going to remove the node from the old buckets array, and then we're going to put it to the front of the correct linked list in the new buckets array. Okay, specifically, we're putting it in the correct bucket. And which bucket is that? That's the bucket we found with this index by hashing the key. Okay, fairly straightforward linked code. It turned out students found this much more challenging than we thought it would be. Yeah, so I'm going to go over some of the key mistakes that you'll see. Yes, let's actually switch to here. Yeah, so we've shared this with you all, so you can actually see what the common mistakes are. But one of the common mistakes that you'll see here, Rehash here, is first, in this function, they should not call insert, erase, new, or delete, or clear, because all of these will allocate or deallocate memory, and we absolutely really don't want that. Notice that in our code, we basically moved existing nodes to the new bucket, so you really don't want to call insert and erase. Okay? It's very bad if they do, because we literally told them in the starter code, don't do that. Second, because we're dealing with templates here, you have to be careful about making copies of any type. You cannot assume that K and M are primitives, right? K and M might be gigantic vectors, in which case you absolutely don't want to create copies. For that reason, when you access anything like cur value, make sure that you use constant references to these values, and really to any type of type K and M. K and M might be large, so you cannot make copies of them. You should always use constant references to them. Cool. Yeah, this is what we call structured binding. We're essentially just unpacking the key value pairs, kind of like Python. Next, is their linked list code much longer than ours? If their linked list code is just a ton of lines, then they're probably overcomplicating it. Just comment on that. Last thing to note is this std move. This very last line is simply setting buckets array, which is our member variable, to the new buckets array that we constructed. It turns out here that new buckets array is no longer going to be used. But if you don't have the std move, what this line does is it just copies new buckets array to buckets array. That's kind of wasteful because we literally don't need new buckets array. So why do we have to make a complete separate copy? In this case, you can actually just do std move around the new buckets array. What that does is it casts new buckets array to what we call a R value, a temporary value. And then when the equal sign sees that temporary value, it will successfully move the stuff inside buckets array into from new buckets array into buckets array. Okay, some students might be overzealous with std move everywhere else here. The only place where std move has a performance benefit is here. Okay, so just if they use std move anywhere else, just comment on that. Cool. All right, that's it for milestone 1. Let's go to milestone 2. So what's milestone 2? Milestone 2 is all about operator implementation and const correctness. Let's go over const correctness first. What's const correctness? So the idea of const correctness is that here. And if you typically just write like a standard vector, this will not compile because size is, if you don't declare size to be a const function, then this function we wrote over here won't compile, okay? Yeah, you can see here, you'll get something error message here about const. And the reason for that is because what is a const member function? A const member function is a function that cannot modify its private member variables. You knew this from CS16B. In fact, because it's const, you can only call other const functions. So what is a const object? Well, a const object is an object which, when you declared it, it was const. Okay, that's actually a real little rare because like a const vector is kind of useless. The more common example you'll see is a const reference. So a const reference like this acts exactly the same as if you created a const vector. You cannot try to modify the vector if you pass in a const reference. Okay. Yeah. So then the cool thing about the const functions is that if you have a non-const function, then you're able to call every single member function. But if you have a const object, like the const reference we had, then you're only able to call the constructor, destructor, and the const functions. Okay, so the non-const functions like pushback, you cannot call those. Okay, that's a problem because the at function, which allows us to access elements, we still want to be able to call that, right? If you have a vector, you should still be able to access the elements even if your vector is const. So one fix is, okay, why don't we just add const to the at function? That's bad because recall that the at function returns a reference, right? That allows us to retrieve whatever at returns, like the value, the mapped value, and then you can actually modify that mapped value directly. So we don't want that. Okay, so a second function, okay, why don't we just make the return value, the return reference, let's make that const. That's a problem because then our non-const vector here, then it's not able to modify that when we want to. For example, do we have an example? No, we don't. So then the actual solution to that is you have to have both a const at and a non-const at, okay? So like this, and then what happens here is that the non-const at, the compiler will prefer the non-const version here. So if it's a non-const vector, then the compiler will call the non-const one. If it's a const object, then the non-const one is not available, so it just calls the const one. Okay, implementation of both look exactly the same. Okay, switching over to our code. Okay, so as you can see over here, so in the starter code, students are given an at function. Okay. What's important is they must not change this at function. This at function must stay exactly as it is. And in addition to this at function, they need to add another at function down here, which basically does the same thing that we just talked about. Make this a const member function, and then make sure that the return value, the reference here, is const. The body is exactly the same. They'll know what to do. They just copy paste everything from the before. The important thing is they need to have both. Cool. All right. Let's go over operator overloading. So that's the second part of milestone 2. Sharing screens. Okay. Operator overloading. So operator overloading. The idea is that you can overload operators. I'm sure you all knew this already. In fact, 106B sometimes has student overload the stream insertion operator. Okay. But let's go over operator overloading. When you figure out operator overloading, there are usually some very canonical like implementations, what the header of the operator you're going to overload is. For example, the like plus equals, always has to return a reference, which allows you to chain the elements together. But the only operators that students have to implement are here, indexing. So indexing takes in a key and it returns a reference to the map value, kind of like what a map does. Stream insertion, that allows you to print map. It's unordered, so the order that you print the stuff doesn't matter, but we do specify a format they have to print it. It's exactly the one used in Linux XP. And then finally, the equals and not equals operator. Okay, cool. All right, first thing you should check is you should check the .h file. Okay, so we mentioned before that the .h file must have the bracket operator. Actually, it must have the at function here. So it must have a const version of the at function and a non-const version. Okay, this one is given in the starter code, so you might have to scroll up. So make sure that one is there, but then they have to add their own, this one down here. They must have both. All right, the other function they have to implement, they're gonna have to implement 4 operators. The first operator they have to implement is the bracket operator. The header looks like this. Make sure that their header does not look like this. You might be wondering, hey, the bracket operator is kind of like the at function. Shouldn't you also have a const version? It turns out you can't have a const bracket operator because the key difference between the bracket operator and the at function is that the at function will throw an error if the key is not found. But recall that the bracket operator will perform auto insertion. The CS106B HashMap is a little incorrect in that both do auto insertion, but the STL map, the unordered map specifically, does not do auto insertion for at, but it does do it for the bracket operator. Since it does auto insertion, you cannot have a const function, have it as a const function. So that's why they must not have the second one in their code. They must only have the first one. Yeah, and it's a pretty major error if they do. This is one of those things that the autograder can't catch because this is like, this must not compile, but we can't really test that in an autograder. Cool. The other operator I have to implement is called stream insertion. So that looks like this. The left-hand side is an O stream, and then the right-hand side is a const reference to a map. Make sure that the const is correct. They must have, and just in general, make sure that the parameters have the correct const values. Their headers must basically look exactly like this. The parameters must be const references, except the O stream. All right, they must return a reference to the O stream. You've seen this in CS106B. This allows chaining. It's a friend because the insertion operator has to go through the map itself. So that's why we have to declare a friend as a friend. And then we have to declare this as a separate template. The reason is because when you declare a friend, that operator you declared is not part of the class. So you have to separate template types. And because you can't use K, M, and H because that will cause a name conflict with your hash map itself, we just give it a slightly different name. Okay. Finally, the equal signs looks like this. Notice that we're implementing these as non-members. Okay, these are non-member functions. You will see some students implement this as a member function, and that's incorrect. Okay, yeah, we actually comment over here. Make sure that the equals and the not equals, they're non-member functions. The reason for that is a little complicated. We can actually share these slides with you, and you can actually see the general rules of thumb for basically just the semantics of operator overloading. Operator overloading is fairly, like the syntax is easy, right? You can just go online, find the syntax, but the design choice of, there are a lot of different design choices you have to make. Okay, for example, for member functions, if it is a binary operator that treats both operands equally, so the equals operator, like the plus, the equals, the less than, then you should implement it as a non-member and probably a friend. The reason for that is because if you implement it as a member, kind of like the plus equals, so if you implement it as a member, kind of like this, right? When you implement an operator as a member function, the left-hand side is the implicit this, right? That is, let's see, not this one. Where's the plus equals? Yeah, here, right? If you do a plus equals, the left-hand side is the implicit this. That's why you can call these member functions. And then the right-hand side is the parameter. The problem with that is if for equals, then your left-hand side is the implicit this, but your right-hand side is the parameter. That will actually cause some unequal implicit conversion issues. Okay, if you are interested in that, let me know. I can actually go into more detail about that, but that's simply the reason why you don't want to implement it as a non-member, as a member. You have to do it as a non-member. So if they implement it as a member, make sure you comment on that. Cool. All right, that's it for the header itself. Let's actually look at the implementation. So the implementation of the operators, fairly straightforward, but we can actually go over those. So let's see. Let's remove that. Okay, so What should the bracket operator do? Well, the bracket operator, you might expect it's, okay, check if the key is contained. If it is, then insert. Otherwise, insert a default value, right? Kind of like auto insertion, kind of like the hash map. But it turns out that the insert function, remember that it does both, it also does the functionality of contains. So because of that, you actually just want to write, you don't even need an if statement, just write insert this default value. Okay, the default value is just the key and a default constructed type value of type m. Okay, insert that in. What happens is that if the key is not found, then it inserts this value. Okay, and then the thing that's returned is just the default values that was created. But if it is already in the map, then insert doesn't do anything. It just returns the actual key value pair. So this line of code does both. This is much better than calling contains, because when you do contains, it has to go through the entire hash map. And then when you do insert, you have to go through the entire hash map again. That's 2 passes through the hash map, inefficient. So make sure that they implemented this as a single call to insert. A single call to insert that's labeled here. Right. This is a very common STL idiom that 106B just never teaches. Cool. Stream insertion operator, the printing stuff, basically make sure they print it in the correct format. It's hard for this to go wrong. We graded functionality already, but just make sure that it's efficient and it's clean. All right, so this is like a really clean solution. If they do anything absurdly complicated, make sure you flag that. Suggest ways to make it better. Next, the equal sign. So how do you check the equal sign? Well, how we do it is we check that the sizes are equal, make sure that they're equal. If they're not equal, you can just return false. This is important because accessing the size is very fast, but it's inefficient if you had to loop through everything first. So make sure that they do this optimization. Then they have to loop through all the buckets. Okay, they have to go through, like at the right-hand side, go through all the elements and make sure that each element in the right-hand side is also in the left-hand side. So that's what the contains does. Make sure the key is there and make sure that the mapped value of that key is also the same. If either of them are false, then just return false. Okay. Now, one common mistake you'll see students make is they think, okay, I have to loop through the right-hand side and check everything in the left-hand side is there. We also have to do the reverse, right? Everything in the left-hand side has to be in the right-hand side. So they do 2 loops. Turns out you don't have to do that because we check that the sizes are equal, right? Remember in CS 103, we had this proof. Actually, I'm gonna write it in because it's a really cute proof. Remember we had to prove something like if sets A and B satisfy that the sizes are equal and A is a subset of B, then A equals B. Right? This is like something that was done in week 1 or 2. This is basically what we're using, right? If the sizes are equal and if everything in one set is in another set, then we know that the 2 sets are equal, okay? Instead of set, just replace that with the map key value pairs and the same thing happens, okay? So, but some students will, instead of checking this is faster because this is constant time checking, but instead what they'll do is they'll not check this and they'll check this condition instead. Okay, yeah, this is also correct. I'm sure we proved it in 103 as well, but this is just less inefficient. It's efficient because you have to loop through both. Okay, so make sure that they only do loop through once, and then make sure not equals is implemented in terms of equals. So make sure they don't copy paste the entire code here. All right, and that's it. That's it for operator overloading. Okay. Awesome. All right, so if there are any questions, just let me know. This annotated solution is extremely extensive, and then I also give the rationale for each of them, so you can copy paste the code, copy paste these as comments if you want. Lastly, I want to go over the short answer questions. So actually, the solution is pretty detailed, so I don't really not want to go over these, but the thing you want to read for is just go through the answers and make sure that they are close. You can comment on it if they're incorrect, but you don't have to actually tell them what the correct answer is. You can if you want. To save you time, you can just comment saying, oh, this is incomplete. Tell them to watch the video that we released because we literally made a video that goes through all the short answer questions. And we actually gave it to students before the due date, so they could actually watch and answer all the questions. Cool. All right, we're done. For those of you who want to learn a bit more of C++, I'm going to go over the special member functions. Only Ethan will be grading it. By the way, he's teaching 106L next year. He's co-teaching it with Nikhil. We'll announce that in the future. But but since some of you want to learn special member functions, I'll actually just go over that right now. What's a special member function? A special member function it's one of 5 different functions. The destructor, which is given in the starter code, the constructor, also given in the starter code. My bad, there's 6. And then there's 4 other special member functions: copy constructor, copy assignment, move constructor, and move assignment. It turns out that when you want to copy a hash map, you can't just simply use the equal sign. You can't just simply, if you don't declare these, the compiler creates them for you, but the compiler generated one is wrong. The compiler will simply just copy all the members over. But that's incorrect, because if you copy the vector of buckets, you'll get 2 separate vectors, but the contents of those vectors, the front pointers, are the exact same pointers. So both hash maps are pointing to the same nodes, which is bad, right? When the destructor is called, the nodes will be freed twice, which is bad. So you have to declare your own constructors. The constructor's header looks like this. It takes in another hash map. What we do here is this thing is called member initialization list. We initialize all the members. And here we're making everything basically a copy. Size is 0 because later we call insert on each of the elements. We go through all the elements of other and we insert it into this. Okay? Yeah, this is the constructor. We're constructing a new hash map that's a complete copy of the other. Because we use insert, this will allocate its own memory, so the memory is separate from other. Okay? Cool. Yeah, notice that here we're not copying the vector here. Here we're constructing a vector that has size bucket count. Copy assignment is really similar. The only differences are it's not a constructor, so you can't use the sysmember initialization list. You have to do it one by one yourself. Also, you have to free everything that was in this pointer. You have to free that before you actually reassign everything. Okay, if you don't free this, you'll have a massive memory leak. So make sure that they call free. And that's it for the copy constructor and the copy assignment. All right, move is a little more challenging. And if you want to learn more about this, please let me know, because this is like literally my favorite topic in 106L. It's called move semantics, and it's essentially it was developed in C++11. It's the idea of how can we make code more efficient by moving instead of copying? And it's actually fairly complicated about when you cannot do that. Now, but the key idea here is that when you implement the move, you have to take in this thing called an R-value reference. What this does is this move constructor is only called, we call this binding. This parameter only binds to a hash map if that hash map is a temporary value. If it's a temporary value, then we can safely steal its stuff. We can move stuff from it. If it's not a temporary value, we cannot steal its stuff because it might be used later. All right, and then the key thing here is you just call std move. That casts each of these to an R value as well, and then you just pass it to the respective constructors. So this does the moving itself. They have to call std move here. If you don't call std move here, then copies are created instead, which is bad. All right, move assignment, similar, except it's kind of like the assignment thing where you have to call clear. Okay, and that's it for the assignment. Now, I spent a lot of time developing this assignment, and it's a really cool assignment. I recommend that you look through it. In fact, if you have time, if you're bored of the summer, feel free to implement this because this is really interesting. Yeah, okay, cool. And then there's some extensions. I don't think anyone's actually did the extensions. Yeah, because the extensions are pretty difficult. But then you can actually implement it in iterator class. If you're curious about this, let me know. It's pretty interesting. Okay. Lastly, I want to go over, in case anyone's ever interested, I'll actually just quickly go over the code, that's the starter code that we gave them. So we actually gave them all these files. One thing to notice is that there's a test harness. So I was actually trying to use the Qt creator test harness, and it was really bad. So I wrote my own test harness that's given here in tests. And essentially how you can run the test harness is assignment 2. Solution. Okay, you can run it in the command line. So simply press, type in make, and it will, okay, I probably changed something, but that's odd. No member called value in the pair. Huh. That's interesting. All right, but essentially, yeah, in the test harness, you can run a test harness. It's actually kind of slick. And then there are a lot of test cases that you can turn on and off. You might want to turn off a test case because a student might not have implemented that function. So that's why you might want to turn it off. But we did that for you, so you don't have to do that. Kind of like in 106B, you can use the run test harness. You can change that to a 0. What that does is then it runs the student main function, so students can actually test their code. In the test file, you can actually see all the test cases. 106B uses this macro called check true or something. We use this thing called the verify true. It just checks that the condition is true. The nice thing about these is that if one of these is false, it will also print the line number. So I'm super sad I can't demo this right now. It'd be really cool if I could demo it. Hash. CD. Oh yeah, I can probably do that. CD assignment to copy. I made a copy just in case I ever needed to modify it. Yeah, so the test harness looks like this, where you can actually run the test harness, and then if it passes, it will say pass. And then if your code is incorrect, for example, let's actually just make a minor mistake to our HashMap. Let's actually change the rehash function so that it's not right. Oh, that's not supposed to be right. That's not supposed to pass. That's weird. There we go. Oh, the test harness is off. Turn on the test harness. Run the test harness. Yeah, and then you can see that that if it fails, it will tell you exactly which line number in the test file it fails. So here it failed in line 259. We just go to line 259, and you can actually see, oh yeah, verify true. This line failed. Okay. Yeah, so it's a pretty cool. I'm really happy about this test harness. Yeah, and then the extension tests are also over here. Cool. All right. Well, that's it for this video. Hope you enjoyed it. Hope you learned a lot of C++. Let me know if any questions while you're grading. We hope that this is a fun grading experience. And again, thank you so much for offering to grade throughout the entire year. Anna and I, we really enjoy teaching this class, and part of that is because we have so much help from you all awesome section leaders. So thank you so much for helping out, and best of luck in grading. Let me know if any questions. Have a great summer.